In this tutorial, we will be discussing electron dot structures. To do that, you need to figure out how many valence electrons there are, because those are the ones that are actually participating in the bonding itself. They're the ones that electrons are surrounding the nucleus and can be classified as both core and valence electrons. So if we did the electron configuration of boron, for instance, 1s2, 2s2, 2p1. The core electrons are in the first energy level, such as that, which is helium. It's the 2s2, 2p1 that are the valence electrons, so it has 3 valence electrons. Bromine has an electron configuration similar to argon, plus 3d10, 4s2, 4p6. We want the ones in the furthest out. Because 3d10 electrons occupy the valence shell, the outer energy level, but they're considered core electrons because they're totally filled. 10 is the maximum, whereas 4s2, 4p5 is not full. The distribution of valence electrons is depicted with Lewis electron dot structures. The valence electrons are distributed as shared or bonded pairs, and unshared electrons or lone pairs. The focus is on how the atoms bond to a center atom. According to the Lewis theory, when atoms bond, they tend to gain, lose, or share electrons to result in a full shell or a noble gas configuration. For instance, here, oxygen has 6 electrons before it begins. We have 2 lone pairs, and we have 2 single electrons. If it bonds to hydrogen, hydrogen shares his electron with oxygen to give it a total of 8 around the oxygen, which would then be an octet. Notice hydrogen can only form a duet. This is because there's not enough room around hydrogen to fit 8 electrons. It only has a single energy shell. Atoms can achieve the full shell look by transfer of electrons between each other. We're now going to be discussing the ionic bonding. Ionic bonding is the transfer of electrons between atoms. It's the formation of cations, which become positive by losing electrons, and anions, which become negative by gaining. The attractions between the ions are strong and dependent on the size of the cation and anion forming the bond. The stronger the attraction, the larger the lattice energy, and therefore the higher the melting point. Atoms can achieve the full shell look by transferring electrons from one another. The electrostatic attraction is a non-directional. In other words, it's attracted in all directions. So if we have a positive, it doesn't matter where the negative is, because it's going to be attracted to it in every direction. Therefore, there is no ionic model, so to speak. Instead, it's a continuous crystal of repeating ions. Lewis theory predicts ionic compounds should have high melting points and boiling points because breaking down the crystal should require lots of energy. The chemical formula is an empirical formula, which is the most reduced form because it simply gives the ratio of ions based on the charge balance. Now let's discuss covalent bonding. According to Lewis theory, atoms can achieve an octet valence electrons by sharing their valence electrons with each other. The shared electrons would then account towards each atom's octet. Covalent bonding is the sharing. That's the important part of valence electrons, where ionic was giving and taking, forming cations and anions. The attraction between atoms are directional when covalent. The shared electrons are most stable between the bonding atoms. Lewis' theory predicts covalently bonded compounds will be found as individual molecules rather than an array like ionic compounds. So in other words, instead of repeating cations, anions, cations, anions, they're formed in units. Lewis' theory predicts that melting points and boiling points of molecular compounds should be relatively low. This is because it involves the breaking of attractions between the molecules, not the bonds themselves. With ionic compounds, they're actually breaking the bonds, or breaking that attraction between the positive and the negative, whereas these are much weaker attractions. The covalent bonds are strong, but the attractions between the molecules are generally weak. Alright, so let's talk about how to do these Lewis dot structures. First thing you want to do is count the number of valence electrons on all atoms in the molecule. So for instance, if we're looking at carbon, there's a really easy way of looking at the periodic table if they're representative elements and determining how many valence electrons it has. Let's take a step back and just do it the old-fashioned way first. It has 6, so that makes the electron configuration be 1s2, 2s2, there's 4, we need 2 more, so 2p2. 1s2 is on the inside, 2s2, 2p2 is on the outside. That's where they got this from. Notice that there's 2 electrons here and 2 here. So there's a total of 4 electrons. Now the shortcut method is to count the representative rows over. So 1, 2, 3, 4. It's in the 4th row. So therefore it has 4 valence electrons. That's how the periodic table is set up. Let's try that again, but let's try it with NH3. N is right here. It's in the 5th row. So that means nitrogen has 5 electrons. Just to show you how that was done. 1s2, 2s2. That's 4. I need 3 more, so 2p3. 2 plus 3 is 5, and it's in the 5th row. So I can go ahead and do the shortcut if I want. We need to count the number of valence electrons in all the atoms. So I have 3 hydrogens too. So I have 3 hydrogens. Hydrogen is in the 1st row. So I have 3 times 1. So 5 plus 3 is equal to 8 electrons total around this molecule. Arrange the atoms where the most electropositive or least electronegative atom is in the central atom, if one exists. So if there's only 2 atoms there won't be a central atom. Hydrogen is never the central atom. That's really important. So that follows this rule. So hydrogen will not be the central atom. Nitrogen will be. And I'm going to arrange it like it's a box around it. I haven't put any of the dots there yet. That's going to be the next step. So I'm going to put that back up here. That's what we just did in our last step. Draw single bonds between each atom. Remove the electrons used to form these single bonds from the total valence count. So I had 8 electrons total. When it says draw single bonds between each atom, it's referring to drawing it from the outside in. So we have 1, 2. Each bond is worth 2 electrons. 1, 2, 3, 4, 5, 6. Remove those electrons from our final count. So now we have 2 electrons left. Place the pair of electrons around the peripheral atoms until octet is reached. Remove the electrons used in each step from the total valence electron count. Now remember, hydrogen can only do a duet. It can't do an octet. So we're going to say that this is full here. There's 2 here. There's 2 here. These electrons are counted to both the nitrogen and the hydrogen. So it's going to be around here too. So let's redraw that. I have hydrogen, hydrogen, hydrogen. I started off with 8 electrons. I used 6 from the bonding, so I have 2 electrons left. All my hydrogens are duets, so I don't have to go on with those. If any valence electrons are left, place those electrons around the central atom until octet is reached. So I have 2 electrons, so I'm going to put them right here. Remove the electrons from this step from the total valence count. So minus 2 electrons. That brings me to 0. We use these electrons to count the duet. We're also going to use them to count the central atom. So 1, 2, 2 here, that's 4, 2 here, that's 6, 2 here, that's 8. So I have a total of 8 electrons, which means I have a full octet here. Check for octet with each atom. Hydrogen will never reach octet. If octet is satisfied for all atoms, then you are done. Because nitrogen is now an octet, we're done here. So the final figure looks like this. There are a few exceptions to the octet rule. Specifically, hydrogen, lithium, beryllium, and boron attain an electron configuration like helium, which only has 2 electrons, which is a duet, not an octet. Lithium loses 1 valence electron. Hydrogen shares or gains 1 electron, though it commonly loses 1 electron to become H+ and have nothing. Beryllium loses 2 electrons to become beryllium 2+, though it commonly shares 2 electrons in covalent bonds, resulting in 4 valence electrons. And then finally, boron loses 3 electrons to become B3+, though it commonly shares 3 electrons in covalent bonds, resulting in 6 valence electrons. Now to go the other direction, expanded octets for elements in period 3 or below, so we're talking about ones that actually consist of d orbitals, so here on down, use empty valence d orbitals. So that means that they can actually have more than an octet. Alright, so let's practice. First thing we want to do is figure out how many valence electrons we have. We have hydrogen and we have fluorine. Let's count across. 1, 2, 3, 4, 5, 6, 7. Hydrogen has 1. Fluorine has 7. So we add those together to have 8 electrons total. There is no central atom here because there's only 2 atoms. So here's 2 electrons for the bond. We have 6 electrons left over. Hydrogen can only have 2, so that means the rest of them have to be in fluorine. Spread them out first, and then go back and pair them up. Now we have 2 for the bond, 4, 6, 8. These are bonding pairs. These are lone pairs. Let's try this one. CCl4. This is a little bit harder. We have carbon and chlorine. 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 4. There's 1 of them. We have 4 chlorines now, which are right here, which is 7. So 4 times 7 is 28. So that means we have 28 plus 4, which is 32. The next thing we want to do is put the least electronegative element in the center. Carbon is here, chlorine is here. Carbon's furthest away from fluorine, so that means carbon's going to go in the middle because it's the least electronegative. Then we're going to put chlorine all around it. And we're going to pair those up to the central atom. We have 2, 4, 6, 8 electrons used. That brings us to 24 electrons. So now we need to put them around our chlorine. We go the outside first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We don't have any more electrons left over. Let's double check that everything's an octet. Chlorine has 2, 4, 6, and then 2 from the bond. 2, 4, 6, and 2 from the bond. 2, 4, 6, and 2 from the bond. And 2, 4, 6, and 2 from the bond. So we have a total of 8. Now carbon, 2, 4, 6, 8. We're all good because that's 8 as well. Do one last one just to make sure we're on the ball. Carbon. We have 1, 2, 3 carbons. Carbon is right here. 1, 2, 3, 4. That's going to come out to be 12 valence electrons. Hydrogens, 3, 4, 5, 6. That has 1 valence electron. Add those up. That comes out to be 18 electrons. First, one thing we need to do is make sure that we have the least electronegative element in the center. But since hydrogen can never be in the center, that means carbon is going to be in the center. And the carbons are going to be bonded to each other. Now we're going to put the hydrogens around it. When it's written like this, a little hint is this goes with the atom in front of it. So hydrogen has 3 right there. There's 1 hydrogen that goes in here. 2 hydrogens that go with this one. Alright, let's see how we're doing with our electrons so far. 2, 4, 6, 8, 10, 12, 14, 16. The duets, 2, that's good. 2 here, 2 here, 2 here, 2 here, 2 here. Alright, so those hydrogens are okay. Now let's take a look at our carbons. 2, 4, 6, 8, that carbon's okay. 2, 4, 6, that needs 2 more electrons. 2, 4, 6, that one needs 2 more electrons. So these both of these carbons need 2 more electrons. We only have 2 more electrons to give. So that means that they actually end up sharing those 2 electrons. So that way they can both be a full octet. 2, 4, 6, 8. 2, 4, 6, 8. Now that just gives you an introduction to Lewis dot structures. But just like stoichiometry and balancing chemical equations and things along those lines, the only way to get good at this is to practice. The more you practice, the better you'll be.